The infinite limit are those that have a value of positive, negative, infinity, where the function goes without bound as it approaches some value a. So, let f of x be a function that can be defined on either side of a point a and may or may not be defined at a. So, f of x as x approaches a is equals to positive infinity, and f of x as x approaches a is equals to negative infinity.
We will take a look at limits whose value is infinity or minus infinity. These kinds of limits will show up fairly regularly in later sections or in other courses, so you'll need to be able to deal with them when you run across them. The first thing that we should probably do here is to define just what we say when we mean that a limit has a value of infinity or minus infinity. We say limit of f of x as x approaches a is equals to infinity. If we can make f of x arbitrarily large for all x sufficiently close to x equals a from both sides without actually letting x equals a. We say limit of f of x as x approaches a equals negative infinity. If we can make f of x arbitrarily large and negative for all x sufficiently close to x equals a from both sides without actually letting x equals a. Let's start off with fairly typical example illustrating infinite limits. We're going to be taking a look at a couple of one-sided limits and normal limits as well. In all three cases, notice that we can just plug in x equals 0. If we did, we could get division by 0. Also recall that the definitions above can easily modify to give similar definitions for the two one-sided limits, which we'll be needing here. Now, there are several ways you could proceed here to get values for these limits. One way is to plug in some points and see what the value of a function is approaching. In the preceding section, we said that we are no longer going to do this, but in this case, it is a good way to illustrate just what's going on with this function. So here is a table of value of x from left and right. Using these values, we'll be able to estimate the value of two one-sided limits, and once we have done that, we can use the fact that the normal limit will exist only if two one-sided limits exist and have the same value. From the table, we can see that as we make x smaller and smaller, the function, x gets larger and larger and will retain the same sign that x originally had. It should make sense that this trend will continue for any smaller value of x that we chose to use. The function is a constant, 1 in this case, divided by an increasingly small number. The resulting fraction should be an increasingly large number, and as noted above, the fraction will retain same sign as x. We can make function large and positive as we want for all x sufficiently close to 0 while staying positive. Likewise, we can make the function as large and negative as we want for all x's sufficiently close to 0 while staying negative. So from our definition earlier, it looks like we should have the following values for two one-sided limits. Another way to see the values of two one-sided limits here is to graph the function. Again, in the previous section, we mentioned that we won't do this too often as most functions are not something we can just quickly sketch out, as well as the problems with accuracy in reading values of the graph. In this case, however, it's not too hard to sketch a graph of the functions, and in this case, we'll see the accuracy is not really going to be an issue. So here is a quick sketch of the graph. Ta-da!
So, we can see from this graph that the function does behave much as predicted that it would be from our table of values. The closer x get to 0 from the right, the larger. In the positive sense, the function gets one closer x gets to 0 from the left larger. In the negative sense, the function gets, and finally, the normal limit in this case will not exist, since the two one-sided limits have different values.
So in summary, the values of the three limits are there. Limit of 1 over x as x approaches to 0 is equals to positive infinity. Limit of 1 over x as x approaches to 0 is equals to negative infinity. Limit of 1 over x as x approaches to 0 is equals to does not exist. Let's start with the right-hand limit. For this limit, we have x is greater than to 4, then 4 minus x is less than to 0. Also, 4 minus x is approaches to 0 as x approaches to 4. So, we have a positive constant divided by an increasingly small negative number. The result will be an increasingly large negative number, and so it looks like the right-hand limit will be negative infinity. For the left-hand limit, we have x is less than to 4, then 4 minus x is greater than to 0 when And we still have from minus x is equals to 0 as x approaches to 4. In this case, we have a positive constant divided by an increasingly small positive number. The result will be an increasingly large positive number, and so it looks like the left hand limit will be a positive infinity.
Substitute 0 to x, so it becomes 8 over 0 cube, and so we notice that 0 has a negative sign, so therefore the x is approaches to 0 to the left. That means the answer will be negative infinity.
We'll just need to substitute the value of x to 3, so it will become 3 plus 2 over 3 minus 3. After we substitute, we need to solve the 3 plus 2 over 3 minus 3, so the results will be 5 over 0. Let's now look at the only one constant, which is positive 5, and the x approaches to the left, so that means the answer will be negative infinity.
So we have here an example for you to understand it more. Limit of f of x as x approaches to 3 from the both sides. Substitute the value of x to 3, so it will become 7 times 3 over 3 squared plus 1 plus 6 times 3 over negative 9 plus t squared. Do the multiplication and it will become 24 over 10 plus 18 over negative 9 plus 9. After that, we will now solve it, and the result will be 21 over 10 plus 18 over 0. The answer is also positive infinity because of its rule.
So, for you to fully understand the theorem 4, we have some example for you. So, limit of x over 2 plus x times x squared over 1 plus 2x as x approaches to negative 2 from the left. So, the first thing you need to do is to get the value of x, which is negative 2. So, it will be negative 2 over 2 minus 2 multiplied to negative 2 squared over 1 plus 2 times negative 2. After the substitution, let's now solve the exponent and do the multiplication. So, it will be negative 2 over 0 from the left multiplied to 4 over negative 3. We notice that the final answer has different sign, and there's a rule of multiplication that if the answer is different, the answer will be negative infinity.